Sir, please start, sir. We are already on. Sir, please start, sir.
শোনা যাচ্ছে আমাকে?
হ্যাঁ, শোনা যাচ্ছে।
হ্যাঁ, শোনা যাচ্ছে? Okay. Good morning, everyone. Thank you for joining us today on this. Okay. Thank you for joining us today on this webinar spanning 2 days. Today is the first day. I must say we are truly delighted with the kind of response that we receive attending this webinar at a time when webinars are organized quite heavily all over the places. I, Dr. Ramanathan, an assistant professor at Ramakrishna Mission Vidyamandira Chemistry Department. On behalf of the Department of Chemistry at Ramakrishna Mission Vidyamandira, I welcome you today. I wish we could host you at our beautiful campus right beside the Belur moat, but in the current situation, we are left with no choice in the current. Not just us, the humanity is going through an unprecedented strange time. So strange it is when a simple door handle, we think, is infested with unseeable tiny blobs dotted with suction pads waiting to fasten themselves onto our lungs. And over this months, we have become quack epidemiologists, virologists, or statisticians. Who among us is not secretly praying for a miracle? And which priest is not secretly at least submitting to science? So science, we are here to listen about atmospheric science today, and we have two speakers. Today, Dr. Aparajeo Chattopadhyay from University of Colorado Boulder, and tomorrow, Dr. Vidyamanidya from NIT Jaipur. In our virtual studio, we have our head of the department, Dr. Vidyamanidya, our principal, Swami Ekocittanandaji, our vice principal, Swami Mahaprabhyanandaji, the convener, Dr. Shahid Riaz, and of course, our two speakers, and me. Although we are concerned or panicked about the pandemic today, there is a much bigger threat looming in the horizon. That's climate change. And our atmospheric composition has to do a lot with it. Atmospheric chemistry is an area that is a little less talked about in the traditional realm of chemistry, but it is an extremely important subject given its immense impact on our lives, as well as other terrestrial and aquatic life forms. In this 2-day seminar, our distinguished speakers will give us a glimpse of this unforeseen world, and it will help us cherish and appreciate the diversity of chemistry. That being said, I will request our principal, Swami Ekocittanandaji, to give introductory remarks about the college and the webinars, without whom this seminar was not possible. So I'll request our principal to say a few words.
Om Sahana Bhavatu Sahanau Bhunaktu Sahaviryam Karavavahai Tejasvinavadhetamastu ma vidvishavahai. Om Shanti 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 Hari Om. Respected Professor Aparajeo Chattopadhyay and Professor Vidyamanidya, honored guest Professor Tropospheric, esteemed members of the Department of Chemistry Vidyamandira, and my dear students, my respect, love, and good wishes in due places. As mentioned by Anirvan, we would have been much happy to receive Aparajeo and Biman Babu inside the campus, but the impending situation does not permit us to do so. Anyway, the Bhagavad Gita mentions that among the all possible ligas, all possible penances that one can conceive of. Penance done through inculcation of knowledge, jnana yajna. That is the supreme one. And that's what exactly we see today. All the scientists, all those are there in the educational arena. They continue their journey on the same track, even though the situation suggests to do something else. And that's has been the story with Vidyamandira as well. In course of its journey of 79 long years, Vidyamandira, as envisioned by the pathfinder Swami Vivekananda, actually Swami Vivekananda coined the very term Vidyamandira, and he even mentioned the location to his dearest disciple Sharathchandra Chakravarti, that towards the southwest corner of Belur come up an institution wherein every effort will be done to harmonize Western science and technology with Eastern mode of education, Eastern mode of Guru Grihavasa. So Vidyamandira has been trying to do that residential setup. Students stay here itself, and we do try to harmonize the two that Swamiji dreamt of and instructed us. So we're happy that in this Corona situation, almost all the departments have organized webinars throughout the last 2 months or so. Chemistry department had one only a fortnight back, and that was a very successful one. And I do hope and pray that the Holy Trial that today's seminar as well becomes very much successful, and interactive session will definitely be there, and that will definitely be useful to all these beloved students. Once again, I welcome Professor Aparajeo Chattopadhyay and Professor Vidyamandira, and do hope that they come inside the campus one day when situation becomes normal. Thank you. Om Shanti 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 Hari Om Tat Sat Shri Ramakrishna Pranamastu.
Thank you, Maharaj. Now, I'll request our Vice Principal, Swami Vidyamanidya to say a few words before we go into the course section of the seminar.
Thank you, Anirban. Om Namo Bhagavate Sri Ramakrishnaya. First of all, I would like to congratulate all the faculty members of our Department of Chemistry, especially with Brahmachari Ishatma Chaitanya Ji, our Jit Maharaj, for organizing such a wonderful webinar dealing with the atmospheric chemistry of acetone and ammonia, even under this dangerous COVID-19 worldwide pandemic. Well, being a person, basically, I am from molecular genetics background, so invariably my interest goes on the biological aspects of this acetone chemistry, though I know very little, but I also deal with some area in environmental science courses. So, as we all know, acetone is a very common atmospheric gas that has a very significant impact on our atmospheric chemistry. We know that it is useful to degrade a greenhouse gas like methane. And however, its source is yet to be properly quantified. And this acetone is present nearly all organs and tissues within our human body. And it is produced as an energy source following the metabolic breakdown and utilization of stored fats in the body of humans and rodents and many times other mammals. And of course, we find that acetone is excreted in exhaled breath, and our natural sources of acetone in the air emissions include the vegetation, well, evergreen vegetation, of course, volcanic eruption, forest fires, and so on. And as I mentioned, that anthropogenic emission mostly the sources of acetone include chemical and manufacturing industries like vehicle exhaust, biomass, and the plastic burning and pulping and refuse combustion, tobacco smokes, and so on, landfill, of course. And in human and other animals, we find the toxicity endpoints associated with the acetone inhalation include the acute irritation of respiratory tract and eye and minor neurological disturbances. But very little chronic inhalation data for humans and animals were identified, and it is likely to because it is likely due to the low chronic toxicity and endogenous nature of this acetone. So, with this very brief note, uh, I would like to invite our today's speaker, Dr. Aparajeo Chatterjee, and of course, tomorrow we'll be having Dr. Biman Bandyopadhyay with us to discuss with the atmospheric chemistry of ammonia. So, once again, I would like to congratulate our faculty members of Department of Chemistry, and I wish a great success of today's and tomorrow's sessions. Thank you, everyone.
Thank you, Maharaj. So it is majority of the gas molecules in our atmosphere is nitrogen or oxygen, but there are hundreds of gas species have been detected, the lifetime of which may be fraction of seconds to hundreds of years. They may be in trace amounts, but they drive much of the chemistry in the atmosphere. And they could be natural or anthropogenic in origin, but some species have deleterious impact on human health, and exposure to elevated concentration leads to increased mortality or morbidity. Now I'll request the convener of this seminar, Dr. Riaz, to introduce our speaker to the audience, and then we can hand over the microphone to our speaker and get into the actual presentation.
Thanks everyone for letting me have the opportunity to introduce Dr. Aparajeo Chattopadhyay, the speaker of the current session. Dr. Chattopadhyay did his PhD in 2018 under the supervision of Professor Taposh Chakraborty at ISCS. Subsequently, he joined National Oceanic and Atmospheric Administration Chemical Science Laboratory at Colorado, US, where he is right now working as a postdoctoral fellow. His research interest includes photochemical studies of gas reactions with emphasis on atmospherically significant radical reactions. Currently, he is engaged on studies that involves measuring atmospheric lifetime, infrared spectra, and global warming potential of perfluorinated compounds to assess their suitability as replacements of CFCs and halon compounds. As students of chemistry, we are all aware of the role of CFCs in ozone layer depletion. Yet for various reasons, mainly financial, we are still struggling to fully replace these gases as refrigerants. Here lies the potential applicability of the current endeavor of Aparajeo's group. Today, however, he will be discussing the photo-oxidation of acetone in the gas phase from an atmospheric chemistry perspective. With this preamble, I would now invite Aparajeo to the virtual dais for his presentation.
So, hello everybody. Am I audible clearly?
Yes, I think so.
Yeah, I think. So, can you present my slides? And I think it would be better if everybody is muted.
Yeah.
Good morning, everybody. I hope all of you are staying well during this trying time. I wish and pray everybody's happy and healthy stay. Firstly, I would like to acknowledge the organizers of this webinar and the chemistry department for organizing this webinar and giving me this opportunity to present my work here in this great academic institution. A special thanks to my dear friend Jidda, who initially showed his interest in my research work. So today, I'm going to talk about photooxidation of acetone in the gas phase from an atmospheric chemistry perspective. Now, I've been told that the primary audience of this webinar are the undergraduate and postgraduate chemistry students. So I'll try to present my research and the necessary concepts in simple terms as far as possible, but I'm sure you will have many questions for me, so just note down whatever questions you have and you can ask me after my talk. So again, before starting my talk, I would like to just test whether I'm audible properly. Can you confirm in the chat? Okay. So here is the outline of today's presentation. I'll start with introducing atmospheric chemistry. I think most of the Indian universities does not have this subject in their syllabus in the undergraduate chemistry course. Therefore, it needs an introduction of atmospheric chemistry before I present my research work. I'll talk about some basics of this atmospheric chemistry research. I'll show a classic example of an classic atmospheric chemistry problem to showcase the importance of this research field. I'll also discuss about the current direction of atmospheric chemistry. In the next segment, I'll talk about my research on photooxidation of acetone that I have performed during my PhD at ISS Kolkata. I will talk about the motivation behind this work. I'll show you the experimental results, and we'll also explain the atmospheric implications of the results that we have received. Lastly, I'll present a kinetic experiment for measuring the rate coefficients of an atmospherically important reaction between methyl peroxide radical and nitrogen dioxide. Although I have not mentioned about this one in my abstract, but I think I'll have some time to talk about this as well. And this reaction is in fact related to acetone photochemistry, and I'll explain how this is related. So what is atmospheric chemistry? Atmospheric chemistry is the study of different chemical species present in the Earth's atmosphere, and one of the major aims is to understand the different factors that control the concentrations of these different chemical species. Now, these chemical species are present both in gas phase as well as in solution phase, for example, in aerosols or in cloud droplets. But today, I'm gonna concentrate only on the gas phase chemistry. So here is a list of the major gases present in the air. So the concentration of a gas present in the atmosphere are traditionally expressed in terms of mixing ratio, where mixing ratio Cx of a gas X is the ratio between Nx, which is the number of moles of gas X, divided by all the total number of moles of all the gases present. For example, nitrogen, which is the most abundant gas in the air, has a mixing ratio of 0.78 or 78%. The other major gases present in the atmosphere are oxygen, argon, and water vapor, although the concentration of water vapor is highly variable. Other than these four, all the other gases present in the atmosphere have extremely low mixing ratios. Altogether, they constitute less than 1% of the total gases present in the air. For these extremely low concentrations, they are termed as trace gases. Yet, these trace gases are the reasons behind most of the important atmospheric events, ranging from ozone layer depletion to air pollution and so on and so forth. Here I have listed some very common trace gases and their mixing ratios. And you can see that the mixing ratios are in the range of 10 to the power minus 6 or less. 10 to the power minus 6 is also termed as ppm or parts per million. 10 to the power minus 9 is parts per billion. And 10 to the power minus 12 is parts per trillion. Here we are mainly interested in this component, the volatile organic compounds or VOCs. One example is acetone, which is the subject of today's presentation. Now, the components of atmospheric chemistry research can be described by a three-legged stool concept. What these three components are: field studies, laboratory measurements, and atmospheric modeling. So if you have a three-legged stool and you remove one leg of the stool, then the stool can no longer stand, it will fall apart. Similarly, these three components of the atmospheric chemistry research are very much interrelated to each other. One cannot exist without the other two. In field studies, the concentration of different chemical species in an atmospheric region are measured in field campaigns using aircrafts, balloons, sometimes using in atmospheric monitoring stations, even using satellites, using various analytical techniques. Now, these chemical species measured in the field studies, they are atmospherically relevant chemical processes are investigated in the laboratory. This includes measuring the kinetics and products of a chemical reaction, measuring UV and IR spectrum, photolysis quantum yields, aerosol properties, etc. Sometimes theoretical calculations also help in predicting the fate of a chemical reaction, for which laboratory measurement is not possible for some technical reasons. Now, the results of these laboratory experiments, along with some meteorological parameters, are taken as input in atmospheric modeling. One of the major objectives is to check whether the concentration of a chemical species obtained as output in atmospheric modeling matches with the field data. If there is a big mismatch, then there might be some missing sources, be it a chemical reaction or a missed emission. It then needs further investigation. Atmospheric modeling also helps in predicting some important atmospheric phenomena, for example, climate change, air quality, etc. This is how these three components of atmospheric chemistry research operate. Now I'll present a very common and very important atmospheric chemistry problem, the stratospheric ozone depletion problem. I think all of you have some idea about this problem. So what is ozone layer and how it is formed? This figure shows the concentration of ozone plotted in x-axis as a function of altitude or the height from the sea surface. Here you can see that the concentration of ozone is maximum at around 20 to 25 kilometer. This is known as ozone layer or stratospheric ozone because it falls in the stratosphere. Now, how are these ozone molecules in the stratosphere formed? This was first proposed by Sidney Chapman in 1930, who proposed this set of reactions. The process is initiated by photochemical breaking of a oxygen-oxygen bond or molecular oxygen that forms oxygen atom in its ground state, that is triplet state. Now, oxygen-oxygen bond of molecular oxygen is a strong covalent bond, so it requires high energy photons to break this bond. The wavelength threshold is lambda less than 240 nanometer. Now, this short wavelength light is available only in the upper troposphere, upper atmosphere. This plot below shows what wavelength lights are available at different altitudes. For example, in the troposphere near sea surface, that is at 0 kilometer, the lights having wavelength greater than 300 nanometer are only present. The lights having wavelength 240 nanometer or shorter are only present around 30 kilometer or upper, that is in the stratosphere. This is why this process can only occur in the stratosphere, not in the troposphere. Now, the oxygen atom formed by this process reacts with molecular oxygen to form ozone molecules. Here, M is a collision partner, for example, nitrogen. Now, the ozone molecules thus formed naturally in the stratosphere are degraded naturally again by photochemical decomposition. But here, the oxygen-oxygen bond of ozone is weaker with respect to the oxygen-oxygen bond of molecular oxygen. That is why it requires low energy photons, and the wavelength threshold is 320 nanometer. This reaction forms oxygen atom in its excited state, that is singlet state, which releases its energy by colliding with nitrogen or oxygen present in the atmosphere to form oxygen in its ground state, which then can react with ozone to form again molecular oxygen. So there are natural sources and natural sinks of ozone, and there is a balance between the source and sink, and we get a steady concentration of ozone in the atmosphere. So we have a OX family and a reaction cycle where some reactions are slow and some reactions are fast. Now, if you take steady state on this oxygen atom, the steady state analysis will give us estimation of ozone concentration. I'm sure many of you have solved this steady state approximation problem in your chemical kinetics class. So the steady state approximation of Chapman mechanism provides a concentration profile of ozone, which is given here by this solid line. Now, while this successfully predicted the general shape of the ozone layer, but it overestimated its concentration. This dotted curve here is the observed ozone concentration, and this solid line is what we get from the Chapman mechanism. So clearly, there is a overestimation for about a factor of 2. So it was recognized that there might be some other natural degradation sources of ozone. In 1960s, this discrepancy was solved by incorporating HOX and NOx chemistry in the Chapman mechanism, and the observed profile of ozone was successfully reproduced. So in 1960s, the chemistry of ozone in the atmosphere are very well understood. In 1970s, Mario Molina and Seri Rowland predicted that ozone layer can be depleted irreversibly by some synthetic chemicals known as CFCs or chlorofluorocarbons. These CFCs are not naturally present in the atmosphere, they are synthetic, man-made. These CFCs became very popular at that time as refrigerants. Chemically, they are very inert. Their atmospheric lifetimes are few decades. Now, it takes quite a long time, about a decade, for a gas to reach stratosphere from the troposphere. And the lifetime of these CFCs are so large that they can actually reach stratosphere, where in presence of high energy photons, they can undergo photodecomposition. Here I have shown an example of a CFC, CFC12, which can form chlorine atom by photodissociation. This chlorine atom then take parts in a catalytic cycle to destroy ozone molecules. This involves reaction of chlorine atom with ozone to form chlorine oxide, which then further reacts with oxygen atom to regenerate the chlorine atoms. Therefore, one chlorine atom formed from one CFC molecule can destroy many ozone molecules. This prediction was, in fact, proved to be true. A large decline in the concentration of ozone over Antarctica was observed after 1975. This brought a huge concern over the scientists, because if there is a loss of ozone layer, there will be big consequences of the harmful ultraviolet lights coming from the sunlight. So, for example, there might be increased cases of skin cancer. This problem was not only recognized by the scientists, but also by the government stakeholders, and international agreement was signed in 1987, which is also known as Montreal Protocol, to control these CFCs, which later banned the production of CFCs completely. For this important discovery, Mario Molina, Paul Crutzen, and Seri Rowland were awarded the Nobel Prize in Chemistry in 1995. Here, I'll show you a short movie showing the trend of ozone over Antarctica. Here, the concentration of ozone is color-coded. Red means more ozone, blue to violet means less ozone. You will also see a graph. So from 1970s to up to about 1995, a sharp decline in the ozone concentration was observed. I think in 1995, the CFC production was completely banned in developed countries. And very recently, we see a slow recovery of the ozone layers. So this latter part, we are seeing a very slow recovery. Now this right bottom plot, here it is the concentration of CFC12 over time is shown, and you can see that even after banning this chemical in developed countries about 25 years ago, still its concentration has not gone down to zero, because this is a very long-lived chemical. So it will take few more decades to ozone layer to heal completely. This story shows the importance of this research field And it also shows how the different components of the atmospheric research operate. Here I have listed some present challenges in atmospheric chemistry: ozone depletion and recovery. We have to continuously monitor the CFCs and other ODSs. ODSs means ozone depleting substances. For example, last year there was a big buzz about increase in the concentration of CFC11, and it was found that the origin was somewhere in eastern China. Chinese government acknowledged this problem, and they promised to investigate and solve this one. Another important thing is to identify the potential new ODSs and understanding their chemistry. For example, last year, some new chlorinated chemicals were observed over Norway, and currently we are investigating their atmospheric chemistry in our NOAA laboratory to understand whether they are ODSs or not. Another big issue is air quality. We are all aware about the recent haze and smog events in New Delhi. One of the big contributor to this air pollution is again ozone. Stratospheric ozone is good ozone, but tropospheric ozone is bad ozone because it involves in air pollution. One of the major sources of tropospheric ozone is oxidation of volatile organic compounds. For example, methane, which is the most abundant VOC, can be oxidized by hydroxyl radical present in the atmosphere, which can ultimately form ozone molecules by this sequence of reactions. So we have to continuously monitor what VOCs are being emitted into the atmosphere, understand their chemistry, and measure their reaction rates in the laboratory to incorporate those in the air quality forecast models. Another important contributor to this air pollution is aerosols, although the chemistry of aerosols are still not well understood. One of the major contributors to aerosol formation is again VOC oxidation in the gas phase, which forms semi-volatile compounds that can partition to the condensed phase and take part in SOA formation. SOA means secondary organic aerosol. But still, there are some unknown sources of aerosols in the atmosphere that needs to be investigated. Another big challenge is global warming and climate change. We have to continuously monitor the strategies to search for the strategies to lower the increasing temperature of our planet. We have to identify the potential new greenhouse gases and understand their chemistry. We have to understand the radiative forcing by aerosols. Apart from this, there are other challenges too that I have not listed here. For example, biomass burning chemistry, cloud aerosol interactions, and so on and so forth. So atmospheric chemistry is a very versatile, multidisciplinary, and an emerging research field, which is gaining more and more importance with increasing environmental challenges. I know many of you will do research after your postgraduate studies, and I'll strongly encourage you to choose this research field as your research topic. And in fact, we don't really have many atmospheric chemists in India, and we need more atmospheric chemists to combat with these different environmental challenges. So here I have listed some very advanced atmospheric chemistry research groups in India. Professor Tapas Chakraborty at ISCS Kolkata, where I did my PhD research work. Professor B. Rajakumar at IIT Madras, Radiation and Photochemistry Division at BRC Mumbai. So all these labs carry out very high quality experimental studies. Dr. Sinha's lab at Aizawl Mohali, they do some field measurements. Professor Chandra at Nehru Shillong, Dr. Montuke Hajra at SNP, Dr. Biman Bandyopadhyay and Dr. Pradeep Kumar at MNIT. They mainly carry out theoretical studies, but I know some of them are also starting to do some experimental studies. So these are the research groups in India that I know. This is just for your reference, but I think there might be other research groups too, particularly in field studies and modeling studies. So at this point, I hope you have a general idea about the atmospheric chemistry research. So let's now talk about my research, atmospheric chemistry of acetone. Acetone is a very well-known chemical. It is used in your chemistry laboratories as solvents. In fact, acetone is one of the most abundant oxygenated VOCs present in the atmosphere, with natural abundance ranging from 0.2 to 3 parts per billion. Now, the sources of acetone in the atmosphere include vegetation, ocean, anthropogenic emission. Anthropogenic means man-made activities, for example, vehicle exhaust, industrial emission, etc. Ice oil can oxidation also contribute to a major fraction of acetone. Now, the origin of isoalkane is again mainly anthropogenic, so this is basically indirect anthropogenic source. Biomass burning, etc. So, total about 95 teragram of acetone are being emitted into the atmosphere per year. Teragram means 10 to the power 12 grams, so it's a huge amount. So what happens to this huge amount of acetone being emitted into the atmosphere? The sinks of acetone in the atmosphere include both physical and chemical processes. The physical processes are dry deposition, wet deposition. The chemical processes are reaction with atmospheric oxidants. Atmospheric oxidants are hydroxyl radical, chlorine atom, ozone, and nitrogen radical. In fact, hydroxyl radical is so efficient in removing not only acetone but most of the VOCs that it is known as atmospheric detergent. Photodissociation after absorbing the UV radiation of sunlight is another very important removal source of acetone. Now, what are the relative efficiencies or importances of these removal sources? The most important source is the photochemical decomposition, which removes about 48% of the total acetone vapor. Reaction with hydroxyl radical is the next important source, which removes about 28%, and other processes contribute to 24%. Now, another very important parameter in this case is atmospheric lifetime. The total atmospheric lifetime of acetone is the contribution from all these different degradation routes, which you can determine from this formula. Now, how can we determine the individual lifetimes? For example, the lifetime of acetone with respect to the reaction with OH radical is equal to 1 over KOH plus acetone multiplied by concentration of OH, where KOH plus acetone is the rate constant of the reaction between hydroxyl radical and acetone, which can be determined from laboratory measurement. The concentration of OH radicals are found from the field studies. The atmospheric lifetime with respect to photolysis is equal to 1 by J, where J is the first order photolysis rate and is equal to integration over psi, where psi is the solar actinic flux, multiplied by phi. Phi is the dissociation quantum, photodissociation quantum yield, multiplied by sigma, where sigma is the absorption cross section. Again, this sigma and phi, these quantities can be determined from laboratory experiment. For acetone, these parameters are very well known, and the total lifetime of acetone in the troposphere is estimated about 15 days. Another important aspect of these reactions is what is reaction fate. That is, what are the reaction products and what is the reaction mechanism. Here, I'll be mainly concentrating on the photochemistry of acetone because, as I showed earlier, photochemistry is the major degradation route of acetone in the atmosphere. Although the rate parameters of photochemistry of acetone are very well known, but there are some issues on this part, that is reaction fate. So let's discuss the photochemistry of acetone. In this curve, the curve on your right side, this is the UV spectrum of acetone in the gas phase. It shows that acetone absorbs in the wavelength region of 230 nanometer to up to 330 nanometer. Now the left curve is the solar actinic flux curve, and this overlaps with a part of the acetone UV spectrum, which is shown here by this shaded region. So the acetone molecules present in the atmosphere absorb a part of the UV radiation coming from sunlight and undergoes photodecomposition. At tropospherically relevant wavelengths, that is lambda greater than 300 nanometer, this photochemical dissociation occurs by breaking of this CC bond of acetone. At a shorter wavelength, a different photodissociation mechanism operates, which breaks both the CC bonds, but I'll not go to details because that is not atmospherically relevant. Now, this CC bond breaking reaction is known as alpha cleavage or the Norris type 1 reaction. In Norris type 1 reaction, two free radicals are formed, the methyl radical and acetyl radical. These free radicals have very high affinity towards molecular oxygen, which is present in the atmosphere. So immediately they combine with molecular oxygen to form peroxy radicals, the methyl peroxy radical and the acetyl peroxy radical. These peroxy radicals are unstable species because they are radicals, so they immediately take part in different reactions to form different stable end products, and this whole process is known as photoxidation. These stable end products include formaldehyde, methanol, and probably formic acid. I said probably because this is a controversial issue. So what is the controversy? In 1961, Osborne and co-workers first reported formic acid from photooxidation of acetone. But just after 2 years, in 1963, Pearson refuted this claim and stated that no formic acid production was observed in their case. Although they maintained the similar experimental condition what Osborne used. In subsequent years, there were many reports on acetone photochemistry, but this question remains unanswered. For example, in 1984, Calvert and co-workers stated that although formic acid is a expected product of acetone photochemistry, but they didn't observe that, probably because of the use of GC methods, which is not sensitive to formic acid. But why do we care about formic acid so much? Because formic acid is a very important molecule in the atmosphere. It is one of the largest sources of acidity in the global atmosphere. It contributes significantly to the acidity of precipitation. It acts as a major contributor to cloud condensation nuclei. However, all the sources of formic acid in the atmosphere are not well understood. So there are some missing sources. Here I have shown the result of a recent field study performed in US Southeast in 2015. In the left graph, this black trace represents the vertical profiles of formic acid measured in the SENEX field campaign. And the red curve represents the formic acid concentration profile that is obtained from modeling study incorporating all the known formic acid sources. So clearly, there is a big discrepancy between the observed and model data. So almost 50% formic acid's source are not known. It was suggested that photochemical oxidation of VOCs might contribute significantly to these missing sources. So we thought that if formic acid is really a photooxidation product of acetone, then that might contribute to these missing sources of formic acid. Therefore, we decided to reinvestigate the photooxidation of acetone. So this was our main motivation behind this work. For this purpose, we used a very simple experimental approach. Here, the photochemical reactions are performed inside this cylindrical quartz reaction cell, which is kept inside the sample compartment of a FTIR spectrometer. FTIR means Fourier transformed infrared spectrometer, and is surrounded by UVB lamps, which serve as the photolysis source. These UV lamps are narrowband fluorescent ultraviolet lamps, which has intensity maxima at around 311 nanometer. And from this curve, you already know that 311 nanometer is present in the atmosphere, in the troposphere. During reaction, acetone vapor is introduced inside this quartz reaction cell and is mixed with synthetic air. Synthetic air means nitrogen and oxygen taken in 4:1 ratio. So in laboratory, we created a simulated tropospheric condition. We took synthetic air, the pressure was maintained at 1 atmosphere, and we also used the UV lamp, which is relevant from tropospheric condition. The photochemical reaction is initiated by turning on these UV lamps, and the course of the reaction was monitored by recording the FTIR spectra over time to time. So the function of this FTIR spectrometer is to monitor the concentration of different reactants and products over the course of the reaction. So basically, we used infrared spectroscopy as our analytical technique. So I would like to talk a little bit about infrared spectroscopy for the audience who don't have a prior knowledge on this. From equipartition principle, you know that the internal energy of a molecule are distributed among different degrees of freedoms, that is, different molecular motions. Vibration is one such motion, and here I have shown an example of the different vibrational modes of water molecule, the symmetric stretching, asymmetric stretching, and bending. Now, from quantum mechanics, we know that the vibrational energy cannot take any value. It can only take certain values. Therefore, we have different vibrational energy levels. At room temperature, most of the molecules sit at V is equal to 0, that is at ground vibrational levels. Now, if you introduce an electromagnetic radiation whose energy, irradiation, is equal to the energy difference between the two vibrational levels, then the molecules can absorb this electromagnetic radiation and go to the upper vibrational state. Now, this energy falls in the infrared region of the electromagnetic spectrum. That is why it is also called infrared spectroscopy. One unique feature of infrared spectroscopy is that every molecule absorbs at different wavelengths. For example, this symmetric stretching vibration of water molecule comes at around 3700 wave number. Now, if you substitute one hydrogen of water by a methyl radical, then it will become methanol, but this OH stretching vibration mode will no longer appear at 3700 wave number. It will appear at a shifted wavelength around 3680 wave number. So infrared spectroscopy is highly selective. So you can selectively probe a certain molecule in a mixture. Now let us see what are the infrared spectra that we got in our experiment. In this figure, the black trace represents a part of the FTIR spectrum of pure acetone. The red trace represents the FTIR spectrum of acetone after UV photolysis in absence of oxygen or synthetic air. In this condition, the acetyl radical further decomposes to give one carbon monoxide and a methyl radical. The methyl radicals then further combine to give ethane. This row vibrational features around 2150 wave number is the characteristic of carbon monoxide. This blue trace represents the FTIR spectrum of acetone after UV irradiation in presence of oxygen or synthetic air. And here we get many different infrared bands. For example, this vibrational band around 2780 wave number represents the CH stretching vibration of formaldehyde. This PQR structure around 1033 wave number corresponds to the C single bond O stretching vibration of methanol. And this highlighted one, the PQR structure having a Q branch centered around 1105 wave number, is the C single bond O stretching vibration of formic acid. So this infrared signature is the unambiguous identification of formic acid. So we confirmed that formic acid is really a photooxidation product of acetone. In this plot, I have shown the time profile of different photooxidation and photoproducts. For example, carbon monoxide, which is a primary photoproduct, increases linearly with reaction time or photolysis time. Formaldehyde, it initially increases but then remains almost constant over the course of the reaction. Methanol increases almost linearly, and for formic acid, we get a non-linear trend. I'll explain the origin of this trend later. So what are the issues of this reaction? First one is that how can we quantitatively measure the concentration of different products from FTIR spectrum? This is performed by using Beer-Lambert law. The mathematical expression is absorbance is equal to concentration multiplied by sigma, which is absorption cross-section, multiplied by L, which is optical path length. I think you have you read this Beer-Lambert law in your undergraduate course, and you probably encountered a similar quantity in place of sigma. It was epsilon, the molar absorptivity, which typically is used in solution, but for gas phase we use sigma. And this sigma is known for a specific molecule at a specific wavelength. The optical path length L is also known. From FTIR spectrum, you get the absorbance. So then by using this formula, you can get the concentration. Here I have listed the concentration of different products formed in a typical experimental run. The experimental conditions were following: acetone partial pressure at the start was 0.5 millibar. Intensity of light, which you can measure by actinometry, was 10 to the power 12 quanta per cc per second. Photolysis time was 3 hours, and temperature was maintained at 30 degrees. Here you can see that the yield of formic acid is comparable with all other photoproducts, including carbon monoxide, which is the primary product of acetone photochemistry. It indicates that formic acid is one of the major products of acetone. Now, what is the next issue? It is the effect of surface. So, in our reaction chamber, a large amount of surface area is available. So, one obvious question is that whether the formation of formic acid is due to a pure gas phase reaction or there is an involvement of the surface. So how can we determine that experimentally? Experimentally, it can be determined by repeating this reaction in two different reaction cells having different surface to volume ratios. So here we use two different reaction cells. One's surface to volume ratio is half of the other one. On repeating the experiment, we didn't see any change in the yield of formic acid, which confirms that this is a pure gas phase reaction. the only effect of surface is the wall loss of formic acid due to adsorption. So when we turned off the UV lamps, immediately we observed a sharp decrease in formic acid signal and an exponential decrease, which is due to wall loss. So this is why we get this non-linear trend of formic acid, because there are two processes occurring simultaneously. One is forming formic acid by photo reaction, and another is removing formic acid by wall loss. So in our quantitative measurement of formic acid concentration, we have corrected our data accordingly by taking into account of this phenomena. Now, what is the reaction mechanism of formic acid production? As I said earlier, that the peroxy radical reactions are responsible for formation of different stable products, including formic acid. In this case, the most important peroxy radical reaction is the self-reaction of methyl peroxy radical, which forms one formaldehyde molecule and one methanol. It is proposed that formic acid is produced from this formaldehyde either by its own photooxidation. Alternatively, there is a hydroxyl radical present in the reaction mixture, which is formed by the reaction of acetyl radical with molecular oxygen. Now, this hydroxyl radical can directly oxidize formaldehyde to form formic acid, although the rate constant of this reaction is not very well established. So here, formaldehyde acts as a kind of intermediate. The rate of its formation is similar to rate of its removal. That is why we get this kind of profile of formaldehyde. It remains almost constant over the course of the reaction. Now, here is a list of all the different reactions occurring in our reaction chamber during acetone photochemistry. And you can see that it's really complex, about 40, 50 reactions are there. So how can we verify that these are the correct reaction mechanism that we are suggesting? To verify, we took the help of a reaction modeling study, which was performed by using a computer code known as AccuChem. This basically solves a set of differential equations that are formed from the interrelated chemical reactions. So as input, we give reactants, the reactions with their rate constants. The rate constants are mainly taken from IUPAC and NASA JPL databases, and reaction time. As output, we get concentration of reactants and products as a function of time. So here I have shown a comparison between the product yields that we have obtained from experiment and simulation. And you can see that the experiment and simulation data agrees really well, which validates the reaction mechanism that we have suggested. Now, since this is a photooxidation reaction, we wanted to check the effect of oxygen partial pressure over the yields of different products. So we have performed an oxygen pressure variation experiment. And here is the result of this experiment. With increase in the partial pressure of oxygen, the concentration of formic acid increases, the concentration of methanol decreases, while the concentration of formaldehyde remains almost constant. Now, all these three photooxidation products, their precursor is same, the methyl peroxy radical, whose formation again involves a reaction with molecular oxygen. So how can the trend of these three photoproducts be different with partial pressure of oxygen. To have some more insight, we again ran a reaction modeling, and in reaction modeling also we get a similar trend. Now, how can we explain this kind of behavior? This kind of behavior is explained involving the reaction of hydroxyl radical, which is formed by the reaction of acetyl radical with molecular oxygen. Hydroxyl radical reacts with formic acid. It also reacts with methanol, where the products include CH2OH radical and CH3O radical that can further react with molecular oxygen to form formaldehyde, which in turn produces formic acid. So there are some regeneration mechanism of formic acid. That's why it increases, but methanol decreases due to reaction with hydroxyl radical, while formaldehyde remains almost constant because again it acts as a kind of intermediate. This also validates our reaction mechanism again and the our reaction modeling study. Now, reaction occurring in the laboratory is actually quite different from a reaction occurring in real atmosphere, because in real atmosphere the concentration of the precursors are much less compared to what we use in laboratory. The intensity of light is also different. So we wanted to understand what is expected in actual atmospheric condition. For this purpose, we extended our reaction modeling study to real atmospheric condition. In this case, the input parameters that we have taken are concentration of the precursor, which varied in the range of 0.2 to 10 parts per billion. The reaction rates were as used in laboratory reaction modeling, and the photolysis rates were taken from TUV model. Now, the photolysis rate in the atmosphere depends on the solar zenith angle, which is the angle between the direction of sunlight and the vertical. For our case, we fixed the solar zenith angle at 30 degrees. As model output, we get the concentration profile of formic acid as a function of the precursor concentration, that is acetone concentration. And here you can see that the concentration of formed formic acid comes in the parts per trillion range. So it might contribute to these missing sources to some extent. But if we combine all the other different carbonyl chemistry, then altogether they might contribute significantly to these missing sources of formic acid. Therefore, it is also important to study the photo-oxidation chemistry of other carbonyl compounds. Now, our reaction modeling study also suggested that the key chemical step for production of formic acid is actually different in actual atmospheric condition compared to the laboratory condition. For laboratory condition, the most important reaction is the oxidation of photooxidation of formaldehyde, while in actual atmospheric condition, the reaction with hydroxyl radical is the main important reaction. Now, NOx species, NOx means NO plus NO2, are well-known quenchers of peroxide radicals, and NOx species are also available in the atmosphere, particularly in polluted regions. So would it affect the yield of formic acid? To answer this question, we included the reactions of NOx with peroxide radicals in our reaction modeling. To our surprise, we observed an increase in formic acid yield with increase in NO. How can we explain that? This can be explained by reaction of hydroperoxide radical, which is present in the reaction mixture with NO that forms hydroxyl radical which actually helps in production of formic acid formaldehyde. This again shows the very complex nature of the photooxidation of acetone. So in atmosphere, if you want to model this chemistry accurately, you need to know the rate constants of all these reactions accurately. And this was our next motivation. So we decided to measure the rate constant of one of these reactions. So we have chosen this reaction of nitrogen dioxide with methyl peroxide radical. For this purpose, we developed a new experimental method based on time-resolved infrared spectroscopy that I will briefly explain here. So our objective is to measure the rate coefficients for this bimolecular reaction between methyl peroxide radical and nitrogen dioxide. Now, if you remember the integrated rate law of a second order reaction, to measure the rate constant, you need to monitor the concentration change of both the reactants. Now, one experimental trick is to use pseudo first order reaction condition, where one of the reactant is taken in excess compared to the other one. Here, nitrogen dioxide is taken in excess to methyl peroxide radical. Then you need to monitor the concentration change of only one reactant, which is methyl peroxide radical. So by monitoring methyl peroxide radical reaction, you can get the pseudo first order rate constant. And if you know the concentration of nitrogen dioxide, then you can get the bimolecular rate coefficient. So we need to measure two quantities. One is pseudo first order rate constant for methyl peroxide decay and the concentration of nitrogen dioxide. Let's see how this can be done in the laboratory. First, we need to generate methyl peroxide radicals in the laboratory. This is done by UV photolysis of methyl iodide in presence of oxygen. The experiments are performed in a flow reactor. The methyl iodide and oxygen mixture is introduced into the reactor from one end, then it travels throughout the cell and is pumped out from the other end of the reaction chamber. Photolysis is performed using a laser source. In this case, we used the fourth harmonic output, that is 266 nanometer output of a Nd:YAG laser, which travels throughout the length of the cell. And in this laser path, the methyl peroxide radicals are formed. The methyl peroxide radicals are probed using, again, infrared spectroscopy, but we cannot use FTIR spectroscopy here because methyl peroxide radical is a transient species. So we used infrared laser for this purpose. This infrared laser is quantum cascade laser, which emits in the mid-infrared region. This laser was co-aligned with the UV photolysis laser and the transmitted light intensity was monitored by MCT detector. It is a IR detector, and the detector signal was sent to the oscilloscope. You can also see the signal in a computer screen. Now, the quantum cascade laser was operated in CW mode, that is continuous mode. So its output is always on. But the Nd:YAG laser is not continuous. It is pulsed. So the repetition rate of Nd:YAG laser is 10 Hz. So we get one pulse in every 100 milliseconds. So whenever there is a UV pulse from Nd:YAG laser, there are methyl peroxide radicals that are formed, and then the methyl peroxide radicals absorb a part of this infrared laser light. and we get a sharp decay in the infrared signal due to this absorption of this infrared laser light by methyl peroxy radicals. Now, for kinetics purpose, we probed methyl peroxy radical at around 1099 wave number, which corresponds to its O bond stretching vibration mode. Now, when you want to study the kinetics with nitrogen dioxide, then nitrogen dioxide is also introduced in the reaction mixture. Now, in absence of nitrogen dioxide, the methyl peroxy radical decays mainly through self-reaction, but now there is also reaction with nitrogen dioxide, so we get a steeper decay. From this decay profile, we can get this pseudo first order rate constant. So the only other quantity we need is the concentration of nitrogen dioxide. For this purpose, we introduced a third laser, a diode laser emitting at 532 nanometer, and nitrogen dioxide has a good absorbance at 532 nanometer. So this helps us in measuring the concentration of nitrogen dioxide in situ very accurately. This experimental apparatus was developed during my PhD at ISS Kolkata, and here is a photograph of the actual experimental setup, the reaction chamber, the different lasers, and the laser paths. So here in this plot, the dotted profile is the actual methyl peroxy radical signal in absence of nitrogen dioxide. Now, we also simulated this reaction profile by incorporating different decay channels of methyl peroxy radical, and the simulated curve is the blue one, which successfully reproduced the observed decay profile. We also measured a low resolution infrared spectrum of methyl peroxy radical in the fingerprint region, and this in this spectrum there are mixture of two different modes, vibrational modes. One is OO stretching vibration, another is CH2 wagging vibration. But for kinetics purpose, we probe methyl peroxy radical at 1099 wave number, because the laser intensity was maximum at that wavelength. So this plot shows the dotted profile is a typical concentration profile of methyl peroxy radical in presence of nitrogen dioxide. You can see that without nitrogen dioxide, the signal decay takes about 5 milliseconds, but in presence of nitrogen dioxide, it decays within 1 millisecond. Now, this decay curve can be fitted by single exponential decay function, and the fitted curve is shown here as the red line. From this decay curve, we get the time constant, or tau. 1 over time constant is the decay constant, or A. Now, the decay constant A is equal to K1, which is pseudo first order rate constant, plus AD, which is the decay constant of methyl peroxy radical in absence of nitrogen dioxide. And we already know that the K1, the pseudo first order rate constant, is K, that is bimolecular rate constant multiplied by concentration of nitrogen dioxide. So if we plot A versus concentration of nitrogen dioxide, the slope will give us the bimolecular rate constant K, which in this case is 2.45 into 10 to the power minus 12 at room temperature for 305 millibar nitrogen. Now, since this was a new method that we have developed, we wanted to check our results with already available data in the literature. Here I have shown a comparison. These black symbols represents our data, and you can see that it is comparable with all other data available in the literature that use different experimental methods. So this validates our new experimental method. Now, since this is an association reaction, we see a dependence with total pressure. That is why with increase in total pressure, the rate constant increases. This research was published in Journal of Chemical Sciences as a cover article. So if you are interested in it, you can read this in more details. Now, apart from acetone photooxidation, the rate of this reaction is also important for modeling NOx. For atmospheric modeling of NOx, these are the typical reactions being are considered for modeling NOx, and this concentration profile of NOx are observed. Now, it will be interesting to include this new reaction in the NOx modeling to see what effect is there. Another importance of this reaction is the product, which is peroxymethyl nitrate, or PMN. A similar compound, PAN, which is peroxyl acetyl nitrate, which is formed by the reaction of acetyl peroxide radical with nitrogen dioxide. PAN is a very famous compound because it acts as a transporting agent of NOx at upper troposphere. Now, this compound PMN can also be a transporting agent of NOx species at the upper troposphere, but to assess that, we need to measure the rate constants at lower temperature, which is relevant to tropopause. So in summary, formic acid is a major photoproduct in laboratory photooxidation of acetone. Photooxidation of carbonyls might be a significant source of formic acid in the troposphere. OH plus formaldehyde reaction is a key elementary reaction for formic acid production. The rate coefficient for this reaction needs to be investigated. Rate coefficient for methyl peroxy plus nitrogen dioxide reaction was studied by a newly developed time-resolved infrared spectroscopy method. Temperature-dependent rate coefficients for this reaction needs to be studied, and then this reaction needs to be included in NOx global modeling. So if you are interested in our research, you can read these papers that are published. We also studied other carbonyl compounds like cyclohexanone. And if you are interested in atmospheric chemistry, I would strongly recommend reading this book, Introduction to Atmospheric Chemistry by D. Jacob. And this is available in OF for free. So lastly, I would like to acknowledge my PhD supervisor, Professor Tapas Chakraborty at ISS Kolkata, for his excellent guidance during my PhD. Although I didn't show any of my postdoctoral research here, but still I would like to acknowledge Dr. Jim Barkholder at NOAA CSL, who is my current supervisor, who has a big influence on my research. So thank you, and time for your questions.
Thank you, Dr. Chattopadhyay. Thank you, Dr. Chattopadhyay. Am I audible? Am I audible?
Yes.
Okay. Thank you, Dr. Chattopadhyay, for gracing your important work and sharing with us your findings and opinions today. Now we have a distinguished guest in our virtual studio. Dr. Tapas Chakraborty happened to be our speaker's PhD advisor. Professor Chakraborty, can you hear me?
Yes, I do.
Oh, thank you, Professor Chakraborty, for being with us in our virtual studio. And so yes, this is an exciting piece of work that we heard from your former students. And this is an interesting area of science that we less talked about, but extremely important. So since you were here, and we have many students watching already watched the presentation, and there are some professors also. So I'll request you to say a few words to everyone watching you now.
Yeah, so anyway, so Aparajeo being my this direct student, so I don't have much to say about the scientific part, but I have just one small questions to Aparajeo. I followed the lecture that he presented. Now, Aparajeo, that is there any data available, particularly in this field data, that where this rate of photolysis of acetone in the direct field as a function of zenith angle that has been measured?
So can you repeat your question? I think.
Yeah, yes, you see that actually this since the rate of photolysis of acetone in the atmospheric condition, definitely it depends on this zenith angle.
Yes.
Now, most of the cases, the data that is available is some kind of this average value.
Right.
In the laboratory, you can change the intensity of the light, and we can do this experiment, controlled experiment. But what about in the nature? That data is available?
For acetone, I don't know. For formaldehyde, I know there are some this kind of experiments, but for acetone, definitely we can kind of reproduce this data from our laboratory measurements. But what you are saying, whether there is any actual atmospheric experiment,
Yes.
I don't know if there is anything available. For formaldehyde, I know there is this kind of data, but not for acetone. At least I don't know. There might be.
Okay. So second part of the question is, what about the data in the subcontinent, particularly in the presence of different nitric oxides and nitrogen dioxides? Is there field data?
Well, the field data are in general very less available in subcontinents. Particularly, as far as I know, there is almost no data for formic acid or acetone. But I don't have any idea if there is any field data available for acetone in the. Definitely, there are field data available in Europe or in US, but I don't have any idea whether there is any field data available in this part of the world. I know that probably Professor Sinha's lab at Eisenhower, they probably measured some VOCs in using their proton transfer reaction mass spectrometer. I'm not sure at this point whether they measured acetone. Probably they might have measured acetone. So I just need to check.
Yeah. Second question that I have in mind. See, most of these the atmospheric modeling studies, this accumulation of these pollutants are gradual. But if you think about this, because of this lockdown all over the world, particularly in this area, these polluted cities, there is a sudden break.
Yes.
Right?
Yes.
So
yes. So
can the atmospheric these models can it accommodate this sudden break?
Yes, obviously. So this is a great question. And although I don't have much idea about if there is any studies being done in India or in Asia, but definitely in our NOAA laboratory, during this lockdown, they continuously monitored different VOCs and NOx species in the atmosphere, and obviously they saw a big change, big gradual change when the lockdown was introduced. And now it is being lifted. Then again, the concentration of different compounds are being gradually increasing. And I know they incorporated this in the modeling study, but results are not yet out, the final results. But I know they probably reproduced this in models too.
So, okay, thank you, Aparajeo. Your presentation was quite lucid. So, I think these others can interact. And it's a very important area of research that has direct societal relevance. I hope that many of the students would be encouraged listening your talk. Okay, thank you.
Thank you, sir.
Thank you, Dr. Chakraborty. Now we'll open this session open the question answer session, and we request our participants who is watching or has watched, please type your question in the chat session, and we'll read it out to Dr. Chattopadhyay. I know one of our students, former student Soikat Pandit, he said here that, is there any effects of clouds in atmospheric modeling? If yes, then how it would be addressed? I can't hear him.
Sorry. So now, am I audible?
Yes, you are audible now. Should I repeat the question?
No. I heard the question. Yeah, I got it.
All right.
So at the start of my talk, I said that here I am only discussing the gas phase chemistry, but atmosphere is not about gas phase. There are clouds, there are aerosols, and obviously there in real atmospheric modeling, clouds are also included. But cloud chemistry is more complex, and it's still the cloud models are not very well understood. I don't really have what exact effect will be here. There might be, for example, NOx species might have a change in cloud condition. Also, if you have clouds, the intensity of the sunlight will also change. So obviously there will be change if you incorporate clouds in your model.
So clouds are mostly in the stratosphere, right? But things that are happening like in the upper atmosphere, not many clouds, right?
Yeah, that's true. That's true. But the thing is that if clouds can directly hinder the sunlight that is coming from so it can change the intensity of light, and also there are many species that which are exchanged between troposphere and stratosphere. So so there might be some effect, but I can't say exactly what effect will be there in this chemistry.
Okay, so another student, the third year student, Vinit Chhatra, he asked, sir, what is MIR spectrum?
Okay.
It is a new term to me. Yeah.
Oh, sorry. I'm sorry that I didn't explain that. So MIR is mid-infrared spectrum. So the infrared region can be divided into three parts. Near IR spectrum, the NIR, mid-infrared spectrum, MIR, and the far IR spectrum, the FIR. The mid-infrared spectrum in the range of 400 to 4,000 wave number.
Kaustubh Dotto, I'm not sure where he's from. He asked, sir, how greenhouse effect influences atmospheric modeling? That's what he typed.
How greenhouse effect influence atmospheric modeling? Yeah, obviously that's a big field of area. So greenhouse effect, we know that the greenhouse gases, how they affect the increase in the temperature of the of our Earth. But also there are other components like aerosols. They also affect the atmospheric modeling, and we still don't know very conclusively how they affect. So greenhouse gases obviously is a part of atmospheric modeling, but I think your question is not very definite. So atmospheric modeling of we atmosphere model and gas. So we obviously take all the different reactions for that gas. But and when we model the greenhouse effect, the temperature of the Earth, then we consider both greenhouse gases and the impact of the cloud. So it's a very complex thing and still not very well understood.
Okay, we're running out of time. We can entertain two more questions. One is on the screen right now. What is the difference in atmospheric chemistry during and after climate change? And then we can take another two maybe, but that's all.
So before and after climate change, that's a very interesting question. So first we have to define what is before climate change and what is after climate change. If we think about the greenhouse gases, mainly carbon dioxide, that started increasing after the Industrial Revolution, 1970s. So at that time, our atmosphere was different. It was much cleaner. The temperature was, I think, in this century, we gained about 1 degree. The average temperature of the Earth was increased by 1 degree. So, and obviously, the temperature changed after climate change, and it's still changing. It became more polluted with the increase in greenhouse gases. So obviously, atmospheric chemistry was much cleaner before the greenhouse gases, and now we have many greenhouse gases. So climate is changing, temperature is changing, our atmosphere is becoming more polluted. That's so obviously there is a certain change.
Okay, then this is also our just ex-students just passed out. Deep Kumar Devnath, his question is: photochemical oxidation can produce carbon monoxide, can help greenhouse gas. Is there any effect?
So it's a fantastic question. I actually never thought from this direction. Now, if you see, actually, photolysis, in fact, produces carbon monoxide. So in acetone photochemistry, one of the primary photoproducts is carbon monoxide. But when photooxidation occurs, there are some secondary sources of carbon monoxide. And this is a very interesting question. It is interesting to assess whether what is the quantity of this carbon monoxide. Would it affect the temperature of the Earth? So this is a very good question. I don't have any answer, but this is very interesting to assess this aspect, and this can be done by atmospheric modeling study. So very good question.
Okay, Deep Kumar, so you see there are unanswered questions. So maybe you can address. You just started your MSc. Also goes on another students. Maharaj, can you please put Orko's question on screen? Yes, thank you. How do we control the formation of, I think it's acetic acid, formic acid? How do you control the formation of formic acid as it increases the acidity of our atmosphere? So the question is about control.
So this is also not very clear to me. So how do we control the formation of formic acid as it increases the acidity of atmosphere? So yeah. So for this, we need to know what are all the sources of formic acid. That is still not very well known. So if we think that, and one major source is vegetation, and we cannot control the vegetation sources. We can only control the anthropogenic sources. Like if acetone, if it is still not confirmed, if acetone really contributes, acetone and other carbonyl compounds really contribute to formation of formic acid, then obviously controlling these VOCs will help in controlling production of formic acid. So again, we have to control these VOCs.
So this is the last questions and of our question session. Bipha Mondol has asked, sir, why ozone is divided as good ozone and bad ozone? Kindly explain.
Okay. So as I said, in the stratosphere, the stratospheric ozone that absorbs the harmful part of the ultraviolet light that is coming from sunlight. So it helps the life to exist. It helps. So that is why the ozone that is present in the stratosphere is called good ozone. But in the tropospheric ozone, the tropospheric ozone is bad ozone because it contributes to air pollution. If the ozone concentration is high, and you inhale this, that can oxidize, that can carry out oxidation reactions, and you may have different health problems. So in troposphere, ozone is not good because it contributes to air pollution. But in stratosphere, ozone is good because it absorbs the harmful ultraviolet radiation coming from sunlight.
Okay, there are many questions, curiosity among the participants, but you have to consider that our speaker is talking from the other part of the world, and it's getting midnight. So we will close the question and answer session now, and I'll request our assistant professor, Dr. Ashadullah Mollik, to give a formal vote of thanks. Ashad, we cannot hear you. Ashad. No, Ashad, we cannot hear you. Is that me? Ashad, we cannot hear you. Ashad, can you? No, we cannot hear you. Okay, I think there are some technical glitches. Sorry about it. So thank you, Professor Dr. Chattopadhyay. Oh, is he? Are you back? Ashad. Okay, so sorry about it, Dr. Chattopadhyay, sorry about it. So on behalf of the Department of Chemistry and on behalf of the Vidyamandira family, we express our sincere gratitude for coming us online and presenting your important work in front of us and sharing your opinion and your thoughts. So it would be wonderful if you come back and actually present in person at Vidyamandira, and people can see you, and the kind of work you are doing could be a motivation to our students. Thank you so much.
Yeah, thank you very much for giving me this opportunity. Actually, Belur is a very good place. I visited it several times, and I really like the place. So, yeah, I'd like to visit it again and again. And yeah, thank you.